Alrighty. Hi, everyone. My name is Nathaniel Bandemer, and today I'll be defending my honors thesis. My committee is for my thesis director, Dr. Gennaro De Luca, and second member is Dr. Yanong Chen. Thank you guys so much for attending and helping me out through the course of this project. And my project is predicting tennis matches with machine learning. So we'll go ahead and get started here. Can everyone see my screen?
Yes.
Perfect. Alrighty, let's get started. So for the outline for today, first I'm just going to introduce the project and introduce a little bit about myself and why I came to decide on this topic. Then we'll discuss a little bit about the data that we use to predict these tennis matches, and then some of the models, machine learning models that we use to actually make this happen. And then some of the basic experiments or workflow that went into making this happen. And then, of course, some results and some conclusions based on those results. So for a brief introduction, some background on myself. I'm studying computer science and graduating this spring. And also, I'm a tennis player. I've played tennis my whole life. Grew up playing tennis, care a lot about the sport, very passionate, and obviously very passionate about computer science. So I kind of wanted to combine my passions and explore something that could kind of bring these two worlds together. And some of the goals coming into this year was I didn't really know much about AI and machine learning. It's obviously growing a lot right now, and it's something that I haven't learned too much about in school. So I really wanted to learn by just doing it this year. The other thing too is I do want to kind of deepen my knowledge on the world of tennis as well and learn something about, what statistics are relevant, something that helps not only as a player but as a spectator. And so by doing this project, which the overall objective of it is to predict tennis matches using machine learning, I can kind of bring those two passions together. So let's start by just talking about the data set and some of the features we're going to be looking at in making these predictions. So to start, the data set we're working with is a collection of completed ATP, which stands for Association of Tennis Professionals. It's specifically the men's tour, so it's the men's professional tennis tour. Specifically, we're looking at the date range from 1991 to 2023, as this is where we have all the complete statistics we're looking for our predictions. And so we have all this data, and then we're specifically grabbing matches that are tour level, so we're not including things like qualifying, challengers, etc. We're also not including withdrawals. So if a player retired from the match early, we're not going to consider that. And so with all these considerations, as well as only using matches from players that have played more than 10 matches at the professional level, we come to roughly 80,000 matches total in our data set. So once we have a data set, the key thing is we need to actually extract the features we care about, right? Because a machine learning model needs to look at data that we tell it is relevant in order to learn and find patterns. So a couple categories that we're looking at are general/environment, which are basically describing the match as a whole. And then we have player statistics, which are relevant per player. So we have these per player, and they help to give us a picture of the strength of each player in the match. So to walk through these a little bit, you may have heard that tennis matches are played. I don't know if anyone's familiar with tennis, but tennis matches are played on different surfaces. So you have clay, grass, hard court. So that's like a general feature. We also have like the tournament level. So is this like a Grand Slam tournament, which is like the highest level, or is it a bit lower, like a ATP 1000 or 500? We also have the round of the tournament. So, you have finals, semifinals, quarterfinals, etc. We also have the day. So it's just to give a little bit of context as to when did this event actually occur in the calendar year, as well as a best of 3 or best of 5 sets. To put it simply, a set is one of the main blocks of scoring in tennis. It's what you'll see is like 6-2, 6-3, 6-4, if you're familiar with seeing tennis leaderboards or tennis scoreboards. So some matches you have to win 2 out of 3 sets to win the match, or you have to win 3 of 5 sets. So those are two different categories of men's professional tennis. And then for the player statistics, I won't dive too deep into them, but just a little bit of background on these. Um, they use a rolling average of the last 10 matches in order to calculate averages. So basically, it's going to take the last 10 matches statistics, create these averages, and then those averages will be put in to the match data to be like, these are your last 10 matches to create this data. And then these are included for both players. So both players will have all the statistics I'm about to talk about. And then they are slightly, it's a bit arbitrary, but I did create a little bit of a weighting system that puts matches that happened more recently as a bit heavier in the calculation and more difficult as well. Whereas matches that were earlier on in the last 10 or not as difficult are weighted a little bit less. So to dive into these, a few general statistics about each player, such as their ranking, which is their ATP ranking, their age, and whether they're left or right-handed. And then to get a little bit more technical, these are some of the relevant statistics I chose for an individual player. So we have the percentage of them making their first serve. In tennis, you have first and a second serve. So making that first serve is important because it's often the stronger serve. So you have the percentage of making that as well as the percentage of winning points on the first serve. You also have ace percentage, which is how often you hit a serve and the opponent doesn't return it. Double fault percentage, which is how often you miss both of your serves. And then we have kind of on the opposite end of the court, your return statistics. So how well do you do against the first serve? How well do you do against the second serve in terms of point win percentages? So these are all usually about in point percentages. We also have head-to-head wins. So like how well does this opponent do against this opponent in historical matches, right? And then some other more technical statistics have to do with strength against the serve. So break point saved, faced, and conversion percentage, which I won't dive too deep into those. So these are the features that we're going to be extracting and using to train our model. So now let's start talking about the 3 models that we used for this project. So the first model is one of the most standard simplistic classifiers in the world of machine learning. It's the logistic regression model. It's built off the principles of a linear regression model. And to put it simply, a linear regression model generates a continuous outcome. So, any number, it could be negative, positive, whatever, you can view it as it's on a line. So you have your y-axis and x-axis, and it's a point on a fitted line. So a linear regression is a linear line that's fitted to the data points. So where the x is the features and the y is the output. So the logistic regression is built off of this concept, but it makes it so that we can actually make this into a classification model instead of a continuous value. So the way it does this is it converts the linear regression model to a logit scale, but it still has a fundamental linear principle, which is that it has coefficients attached to features, to each individual feature, which kind of represents the weight of that feature. So how important that feature is in making a classification. So they'll either be positive or negative. So in the context of our problem, we're trying to predict a player to win. If it's positive, it means it helps them win. And if it's negative, it means it reduces their chances of winning. And so the key point about this model is that it works on a scale of 0 to 1 based on the sigmoid activation function. So because of this, it kind of gives us essentially a probability of winning based on the features, which is what we want. And then to actually translate this into classification, because our task is who are we picking to win? We're not saying percentage of the chance of the person winning, right? So we're actually saying this person wins the match. So in order to do that, I'm not sure if you guys can see my mouse, but essentially we would draw a line parallel to the x-axis across this graph. And what we would say is if a point falls on this upper part of the curve, we'd classify it as a win. And if it's below that bottom part of the threshold, we'd count it as a loss. So that's what allows us to translate from the percentage to the classification. So this is the general concept of the logistic regression model, which is the first model we use in this project. So before we jump into the next 2 models, they're both gradient boosting machines, which are a bit more complex. So I wanted to explain some background on a gradient boosting machine before I just dive into the models themselves. So gradient boosting machines are an ensemble method. And essentially what this means is traditionally, right, as we just saw with the logistic regression curve, we have a single classifier. We just put our data in and it gives us a single output. A gradient boosting machine does the same thing, but it combines a bunch of weaker models together. So it's not just one, it's an ensemble, is what it's called, or a collection of models. And so these multiple weaker learners combine to create a strong decision. And so the way that this actually works is you can't just throw a bunch of weak learners together and just hope, oh, I hope this will be strong now, right? Because it's not that simple. So instead, each sequential learner, starting with kind of a random decision, is then built to optimize the previous. So what it does is it takes the loss, how bad the previous model was, and it essentially tries to minimize that loss as much as possible. So each sequential learner should, in theory, improve the faults of the previous and decrease the loss. Before I continue to, I want to take a look at this image just to give you an idea of what one of these weak decision makers looks like. It's actually can be just as simple as something like this. It's like a decision tree. So it basically has conditions, like for example, here we say with friends question mark. And if it's a yes, we move to the left. And if we say no, we move to the right. So this is one big tree, right? And as you can see, each tree has subtrees and it creates this complex, collection of decisions and branches. And at the output nodes or leaf nodes, we would have residuals. So the goal of these models is we then take the residual, which is basically the loss or the difference between the correct prediction, and we try to minimize that over time by adding new learners in the model. And so um, once we do that, right, we're fitting to these losses, but we can't just create a model that only works for the data we're currently looking at. So that's where we implement something known as a learning rate, which basically what that does is it says, we're going to make this change, but then cut it by like 100 times or 200 times, whatever, right? Basically what that does, is it prevents us from just simply overfitting to the training data we're looking at. It makes it so that this model slowly trains and slowly learns the trends of the whole data set rather than just one specific instance. And so this process is called fitting or training in machine learning, and this continues over and over again until we decide it should stop. And in our context, what we're going to be deciding is once our loss stops decreasing, we will stop training. That's when we decide that our model is best fit to the training data while still being generalizable to the testing or other data that we have not seen before. So that's kind of how we will stop training. And then by the end of that, we'll have our ensemble of decision makers, which creates the gradient boosting machine. So now we're going to look at two gradient boosting machines that were used for this project specifically. So the first one is called Light GBM, with GBM obviously standing for gradient boosting machine. And so the main concept behind Light GBM is that it employs some pretty novel techniques to prioritize speed. The process of obviously making these trees, deciding where to make decisions, and then combining all of them together is sequential and very slow. And so this makes it so that it just takes too long to train, right, practically. So what we do with Light GBM is we optimize speed as much as possible. And the way this is done is it optimizes the process of split finding, which is basically picking a place in the tree to say, let's make a decision here, let's make a branch to either go one side or the other. So we optimize that process of picking those splits. And in order to do that, we can't just simply, reduce our data set or reduce the number of features. We still need to take all that into account because otherwise we're losing important information. So it's not a trivial problem of, okay, let's just get rid of some data and throw away some features and we'll be good, right? And there are techniques that we'll talk about soon that do kind of try to do that, but this model is built in techniques to handle that problem. So the first technique is gradient-based one-side sampling, or GAUSS. And essentially what this does is it just prioritizes data instances with high gradients, meaning data instances that were very different than the true values. So the easiest way to explain it is they're very wrong. The predictions are very wrong for those. So we want to prioritize those because the model clearly isn't fitted well to that data. And we can randomly drop data that it is well fitted to, because we can just assume the model already knows kind of how to handle an instance similar to that one. So we'll just randomly drop some of those. And so that first technique helps to reduce the amount of data we're processing. And then the second technique is the exclusive feature bundling. And what this does is it tries to tackle the problem of the feature space or dimensionality of the problem. So what this does, with a simple example that doesn't relate to our problem, but just helps to explain this, is assume that we have some features that are mutually exclusive. And for the sake of example, we'll use weather. So we'll say rain, snow, and sun. So when one of those is true, we can just say the other two will be false. Obviously, that might not necessarily be true, but this is the concept behind it. So when we know that those other features will be zero when one of the features is non-zero, we can just bundle those together as the one non-zero feature. So this allows us to kind of reduce the feature space and make it more optimal for training. And the other improvement that we'll also see with our other GBM is it's regularized. So just adding a learning rate in isn't enough to prevent overfitting to the training data. So it also implements regularization techniques to make it so that the model is more generalizable to data it has not seen yet. And pretty amazingly, this model, according to the paper, is 20 times faster than a standard GBM for training. So it's a very, very sizable improvement. So you go from a 20-minute training time to 1 minute. And that's very important nowadays with how much data we're working with. So the second gradient boosting machine we're going to talk about is XGBoost, also called extreme gradient boosting. It's an open source model, and it's considered to be 10 times faster than the standard gradient boosting machine. And of course, is an ensemble method, just like all gradient boosting machines are. And it implements a lot of novel techniques, as you can see in the image. It says about 6 here, but I'm going to explain a few in depth. So the first main technique it uses is parallelism. And what this does is that process of finding those splits and building this tree out is very time consuming. So it does that in parallel. So you can imagine it's building all of these branches at the same time with different threads of computation. So it still needs to build tree by tree because that's just the fundamental concept of GBM, but it does accelerate that process of building the individual trees. And it does this in parallel with different threads. Another few optimizations it has is it's sparsity aware, which is similar to the concept we just mentioned with feature bundling, which is it tries to streamline or standardize the process of when a value is zero, how does it tackle that? There's a lot of zeros in data, so it's sparsity aware, which can help speed up split finding with zero values. It's also cache aware, which helps to prevent cache misses and prefetch blocks from disk. These models are very large, so we need to sometimes store data on the disk or the hard drive and bring that into memory or cache to make things faster. Obviously, computation doesn't even occur in the disk. So you have to be very careful about that, and we need to maximize that throughput between the disk and the memory. So the cache-aware and out-of-core computation techniques help to maximize throughput between the disk and memory. And similar to light GBM, this model is also regularized to help with the problem of overfitting. So that's the basic rundown of the models we used. So now we're going to get into the actual workflow of how we actually made this all happen. Sorry, I'm just going to grab some water really quick. Okay. So the first few techniques we're going to be talking about are in reference to data handling. So they work directly with the features. So the first one is standardization, which is very standard to machine learning. Essentially what it does is it takes every feature and converts it to a different numerical transformation where the mean of the feature is 0 and the standard deviation is 1. And this is a very common practice in machine learning because if you have a bunch of features, like for example for us, we have ranking, which is like a number from 1 to 1,000, whereas you have percentages like first serve in percentage, which is like a 0 to 1 decimal point. So it's important to, at the beginning to standardize these so that the model can view them with equal weights, because we don't want certain features to automatically get extra weighting from the beginning. So it's just a natural process that we do with data sanitization in machine learning. And so the second technique that happens immediately after standardization is principal component analysis. And the objective of principal component analysis is to reduce that feature space, to reduce the dimensionality. As we discussed, that's a big problem with gradient boosting machines in particular for increasing that time it takes to train. So reducing that can be very helpful to improve training times, as well as actually reduce some noise in the data. The way it does this is it essentially takes features and makes linear combinations of them, which are called principal components. And in our project specifically, um, we're trying to keep as much information as we can, right? This is general to all projects, but we're trying to keep as much information as we can. And so one way of viewing the amount of information that we can grab is variance in the data. So the way we generated our principal components was that we wanted 95% of the variance in the data to still be captured by these components. And it turned out for our project specifically, we still needed like 31 principal components to cover all of the variance. So it ended up actually not being super beneficial in our project, but in other projects, it can greatly reduce the feature space and reduce noise in the data. And then finally, for data handling, um, we need to actually train on some data, but also evaluate on different data. We discussed the problem of overfitting to training data, which is like it only works on the data it's seen, but doesn't actually work well on data it hasn't seen. So a common practice, the percentages vary, but is an 80%, 20% split. So we train on 80% of the data, we evaluate on 20%. And specific to our problem, it's time sensitive. And so I'll explain that a little bit. So tennis matches in our data set occurred between 1991 and 2023. So we can't have a model looking at matches that occurred in 2021 and then looking at matches that then occurred in 2017 or 2016 that were before the match we've already seen. We need to make sure we're going through the data in time-sensitive manner, because otherwise that introduces the concept of data leakage, which is that it already knows what's going to happen in the future, right? And especially for a prediction task, we can't have that happening. Um, and you will actually see inflated metrics if you do not do the time splitting. So essentially 80% of our data is from like 1991 to 2014, and then the data we haven't seen is between 2015 and the present, and that's what we evaluate against. So those are our three data handling methods. And then we have three methods that work together to actually train models. So the first one is a prerequisite that isn't required. And in our project, we specifically only performed it for the XGBoost model, which I'll explain later. But essentially, it's called hyperparameter tuning. And the way you can imagine it is one of the hyperparameters I mentioned earlier was learning rate. There's obviously a lot more, but that's one of the simplest ones. And tuning these values is important because it optimizes the ability for the model to fit and have high accuracy. In our case, we were optimizing for accuracy. And so the way this essentially works is it sets some settings, tests the model, sees how good the metrics are, tests a new model with different settings, repeats this process until we find the optimal set of settings. And so that's called hyperparameter tuning. For training and evaluating, there's two methods. There's train test split, which I mentioned earlier, and cross-validation. So for train test split, you fit the classifier to the training set, evaluate against the test set, as we explained in the last slide. And on that test set, you can't just run it and be like, okay, great, it ran. We actually need to get some metrics, right? So we need to actually analyze how it performed on that data. So some common metrics, which we'll dive into detail here in a second, are accuracy, F1 score, and AUC. And we'll get into that in a second. In cross-validation, it takes a little bit of a different approach because it tries to prioritize evaluating multiple different areas of the data, right? So in our test train split, there's only one set of data we test against. In cross-validation, we want to try to increase that. So we make several folds of train test splits. And in our problem, this was a bit, unconventional because we have to be time sensitive. So we can't just make random splits and, for example, make 5 random splits and then just average those out. We have to do it in time sequential order. So the way we actually did it is we took a small training set, took test set, and then a bigger training set and test set. And as long as the test set was future, like in future time compared to the training set, we could use that. And so we ended up going with like 5 splits. And as the training set gets bigger, the model's naturally going to do better because it has more data to train against. And so the earlier splits have lower accuracy, but then as we move on, they get higher. And we take the average as well as the min and maximum for cross-validation. So now we're going to get into the metrics, which are really important because obviously we want to know how our models performed. So the first one, and arguably the one that we are paying the most attention to in this study, is accuracy, because we don't really have an imbalanced data set. So we don't really need to worry about, we do need to worry about the other metrics, and I'll get into that soon, but accuracy is what we care about, right? We want to predict matches correctly with the highest ratio, right? So accuracy is essentially all of the correct predictions divided by total predictions. So it's just how often are we getting these predictions right? And our baseline accuracy that we're going for with our models is 64.3%. Now that might sound very arbitrary, but it's because if you picked the higher ranked player to win every match in our test set, that's the accuracy you would get. So we're going to use that as our baseline, and we're going to hope that all of our models surpass that baseline. So now we're just going to go over some other common metrics. So first, we have precision and recall, which kind of go hand in hand. And I'm going to try my best to use an analogy to explain these. So let's say we have 5 fruits, and 3 of them are apples, and 2 of them are oranges. Precision is our ability to correctly predict that something is an apple in comparison to all of the classes, so including the oranges as well. So for example, if we had uh, we classified 3 as apples and 2 as oranges, and they were actually all apples, we would have a 60% precision. And then recall is specifically just looking at the one class. So we would just look at all of the apples we have, what percentage of them were correctly predicted to be apples. So that would be recall. Whereas precision takes into account the other class as well into its calculation. And therefore, these metrics are kind of combined into one metric known as F1 score, or F1 for short, which essentially just takes the harmonic mean of the 2 metrics and gives us kind of a general idea of the performance of the model on both the positive class as well as the negative class together. And then the last 2 metrics we're going to be discussing is confusion matrix and ROC AUC. A confusion matrix gives us an overall picture of what the model predicted. So in the top left corner, we have where it predicted correctly that it was true positive. The bottom right corner is when it correctly predicted a negative, and then the top right and bottom left are false predictions from our model where we incorrectly classified the sample. And so we'll see those in the next slide for our first model evaluations, and I'll explain it a little bit better there. And lastly, our ROC curve determines the strength of the classifier. I know it's a little small, but the blue point in the top left means that we correctly classify every sample. So every positive is correct, and we're not getting any false positives. But obviously, we're not going to have a perfect classifier, right? So these are some common looking ROC curves for different levels of classifiers. And as you can see, this blue curve here is the strongest because it has the best ratio of true positive rate and false positive rate at different thresholds. So we overall want to maximize this curve, and the best way to measure that is the area under the curve. And the easy way to explain this is, see our random classifier is just a straight line across the graph. Half of that is under the curve and half of it is above. So that gives us an AUC score of 50%. Anything above 50% is better than nothing, right? It's better than random. So we're going to want to see a curve that has that slight curve to it and has a decent AUC or area under the curve. All right, so let's actually get into the results of these 3 models and how they performed with the different test train split and cross-validation. Okay, so our first model, the simplest model, is the logistic regression curve. And before we dive into the numbers, the orange highlight means that it's the highest seen out of all 3 models. And so as you can see on the test train split, which is where we take some data, train on it, and test on the other part, we got okay scores. So we did improve on the baseline by about 0.6% for accuracy, as well as precision, recall, and F1 score are all relatively the same for the logistic regression. And the reason why is if you look at the confusion matrix in the bottom right corner, you can see that it's predicting 0 and 1 at almost the exact same ratios. So you can see that it predicted 0 and 1 correctly almost the exact same number of times, and falsely or incorrectly the same number of times. So that's why our precision and recall are so close, is because it's predicting those two classes very evenly. And our area under the curve score is 71.1% for the test train split metrics. And for our cross validation, what you're going to see is we actually got higher accuracy and pretty good, as you can see, highest average and highest minimum for the logistic regression. And what I think this is from is the logistic regression naturally just fits better with less data. So I think it had a lower minimum accuracy when we had less data to train on. But as we got to larger amounts of data, the maximum could not get as high as the next model we will look at. So overall, okay scores, but we will get into why these scores are not exactly as great as we might have hoped in our conclusions. But let's keep going through the other two models. So for light GBM, we're going to see just an overall jump of anywhere between 0.2 and 0.4% for all of our metrics. And it's pretty nice to see us getting over the 65% mark, because now we're getting close to about a 1% improvement over the baseline, which is great because any improvement shows that the features we gave it are more descriptive than just the player's ranking alone, right? So it's at least relatively understanding this feature space and getting some information out of it. And so you can see we got the highest precision and highest AUC score. And that AUC score metric is really, really good because that's the overall strength of our classifier to a certain extent, right? Depending on generalizing it to other data, that's the overall strength of it. We also see the highest cross-validation accuracy, which is good to see that with the best split of training and test data, we got the highest accuracy we've seen out of all of our cross-validation splits. And so the light GBM model does really well in comparison to the logistic regression curve. The other thing I want us to pay attention to before we get to the last model is notice that it is actually predicting the positive class, or 1, more often than the 0 class. So we do see a slight bias in the model toward that 1. And even though our data set is random and it should be balanced 50-50, there might naturally be an ability for it to become more accurate when predicting the positive 1 class more often, as we can see with the higher accuracy. And so moving on to XGBoost, I want us to first look at the confusion matrix before we look at the metrics, because you'll immediately see an even bigger bias towards the 1 class. And so this model is predicting 1 with a higher rate, which is why we get the higher recall score. It's because it's overall predicting the positive class more frequently. So it's going to improve our overall performance on that 1 individual class. But as you can see, our precision does go down because it's not doing as well with the negative samples. We do get our accuracy about 0.08% higher than light GBM. And our F1 score is also inflated due to the high recall. But I think it's important to note here that 2 main things. One is that we did require hyperparameter tuning for this model. We were getting pretty poor performance, what's considered out of the box, which is with default settings. Whereas it actually required us to find the optimal hyperparameters for our specific data set in order to get these good metrics, and with a very, very small improvement over light GBM. So it makes me question a bit how generalizable this model actually is to different data. But we do see the slightly higher accuracy there. So that is the basic rundown of our metrics. And so now I want to bring us to some conclusions on these results. All right. So first, we'll talk about the best model, which I've already briefly talked about. It's great to see that all models surpass the baseline of 64.3% accuracy, right? Because if they're not surpassing that baseline, is no value to these models, right? They're not more accurate than just picking the higher ranked player. They don't give us, they're clearly not learning anything from the data. So they all are learning and they all are more accurate, which is exciting. And of course, XGBoost did reach the highest accuracy, and of course, accuracy is the metric we care about. So it's obviously, inclines us to pick XGBoost as the best model. But I think it's important to note that it did require hyperparameter tuning to reach this accuracy, and was very poor without that hyperparameter tuning. It was at like 63%. So the light GBM model had the highest AUC, which shows the overall strength of the classifier at different thresholds, better cross-validation results in terms of the maximum accuracy achievable, and did not require hyperparameter tuning, and overall still got over 65% on all the relevant metrics, um, and did not show that implicit bias towards predicting one as well, resulting in the inflated recall score of XGBoost. So overall, I would say Light GBM was the best model. It's also the fastest to fit in comparison to XGBoost. And overall, we're not talking too much about logistic regression because all of its metrics were lower. So it's still a good model, but it doesn't have the complexity that the ensemble decision trees provide us. So now let's talk about the limitations. Why couldn't we see higher accuracy and better metrics for these models? So it's pretty clear, no matter what way you look at it, that the features extracted are just simply lacking in predictive power. Um, Even though the models were able to learn information from these features, it clearly just isn't enough to make significant boosts. And this is part of just the natural unpredictability of tennis. Um, Maybe it's just very hard to predict, right? It's very hard to tell how high we really could go with this accuracy. But another key limitation is when actually analyzing which features these models were paying attention to, they were very heavily inclined to look at ranking and like age and things like that, but very much could not find correlations in the data with environment features. And I think this is a very key limitation because, as I discussed earlier, there's something called a surface, tennis court surface, and certain players excel on these surfaces. You may have heard of Rafael Nadal winning the French Open, which is on clay 14 times, I believe it is. Very high win rate on clay. You have Roger Federer on grass. Um, these players, the surface is very, very fundamental to performance. And the fact that these models are not picking up on those environment features is lacking in predictive power. But we will also dive into now some expansion to see why these limitations are there and some ways we can improve them. So the first key thing is our time intervals. As I discussed, we're just using the last 10 matches to calculate these statistics. It's a pretty limited time window, but it does benefit us in getting that recency of like how well is that player playing recently. But it could be lacking in overall longevity. Like for example, how is that player over the last year? How is that player over their whole career? Potentially, maybe we're not getting the full picture. That player could just be having a weak stretch. Um, and overall, the fluctuation match to match is very relative to the difficulty of the matches they're playing, the opponents they're playing, the tournaments, the surfaces. So it's very difficult probably for the model to fully grasp those statistics and get an accurate view. Um, the other really important point is we are using ranking rather than ELO rating. And I think this is important because ELO rating is what is now starting to be considered the standard to actually evaluate a player's raw strength. Ranking is very, subjective to how many tournaments have they been playing recently, what level of tournaments have they been winning. It doesn't fully take into account the performance as of recent. And just one quick example I want to give for this is you may have heard of Novak Djokovic. He's the #1 ranked player in the world right now. But you have a new guy, Yannick Sinner, up and coming, who was just ranked #3. Now he's ranked #2. Um, so in the ranking, it shows that he's worse than Novak Djokovic. But if you look at ELO, which helps to encompass their actual performance, Yannick Sinner being 24 wins and 1 loss this year, his ELO is very high, higher than Novak Djokovic's. And so I think replacing ranking with ELO could be more informative because it gets a better picture of skill at the time. Additionally, adding more features, maybe looking into other statistics, and maybe things like home advantage, how often has this player been playing, like what is how large is the time window for those 10 matches? Um, things like that could obviously improve performance. Another main expansion idea is a deep neural network because this will help to pick up on those environment features or nonlinear relationships in the data, which could really, really dramatically improve performance as it could pick up on things that these other models are struggling with. Um, and lastly, I would say moving away from percentage-based low-level statistics. When we're giving it just percentages, we're potentially losing out on valuable information. Um, it does help to just give us an overall ratio of how that player is doing, so it doesn't weight heavier if you just played longer matches or something like that. But ratios can be, essentially stripping information away from the models. And so that is my ideas for expansion, and that concludes this presentation. Thank you so much for listening, and please let me know if you have any questions.
So Gennaro, you want to ask a question first?
Sorry, say that again.
Or Gennaro, do you want to ask a question first?
Yeah, I would like to see too if anyone in the audience had any
Uh,
questions as well.
Okay, let's start with Gennaro. Okay, so let me start it with the questions. Then Gennaro has a problem with the math. The first question is, you did not give presentation on related work, what other people have been doing at the beginning. So I just wonder whether I also haven't seen your thesis, and I want to check, did you do some research, like for example, ESPN, for most of games, they have a prediction, like, so they have a percentage. Have you looked at how they make the prediction? Do they use also machine learning, or they just use simple statistic? And have you done some of the related work research?
Yeah, so I did some research on other machine learning projects in this domain. And so I've seen some examples of what other people have done for their features. And one example I saw moved away from like point statistics and was looking more at like wins. So who's the play like how many wins does the player have recently, as well as in the last month or year. And it also includes things like I mentioned, the how many matches has the player played recently, has there been a big gap, so things like home advantage. And in general, I've seen metrics range from 65% to 67 to 68%. When you add other metrics I've seen is people have used bet maker odds, like they've actually incorporated the betting houses that are pushing out odds and added that into their models as well. So I have seen related work that has had similar to improved performance, but I've also seen that they've used deep neural networks and things like that for those calculations. So
Okay,
um,
that's very good. Yes, so that's what my point is. When you submit your DFAs, you do need to include the section on related work. Basically, there are two parts you need to cover. One is obviously the related technology, the machine learning method, other models. Another one is application specific related work, what other people are doing similar things like sport, right? I checked ESPN. I do not see the tennis prediction of player, but I do see football
mhm,
and basketball. They always have the prediction. So maybe, yeah, you can search whether there are tennis. If there's a low tennis, that will be a good motivation. You can tell ESPN to say, hey, I do have a model. You could also add
mhm.
tennis player prediction out there, use your model. So that's, you can say, yeah, because I don't see they have this one.
Right.
Obviously, the team sport, they will have more statistic. Of course, yeah, that's come to my second question is, maybe that is also reason the ESPN and they don't put the prediction there because the data is very limited
Mm,
for single player, not like the team player, because the team players, they have a lot of players and their injuries, their status, so they can make some kinds of reasonable prediction. So therefore, my suggestions for you, if you want to do some future work, how can you basically extend your data set? That is the that is one of the research you need to if your data is not sufficient. Yeah, because tennis, yeah, you can say that most players play for a few years, some can play 10 years. So no matter what, from machine learning big data processing perspective, the data is very limited for each player. So what you can do is like what we do recommendation for product reviews. What we do is we are grouping similar items together. You can probably learn which players are very similar. They are close to each other, their characteristics, their strengths, their height, their style, their win-lose chance. You start to group those together, then you can start share or merge their data into a group of similar players and then start to use those data to make more or data rich prediction. So that is what the AI big data domains are doing in such a way. That's just a suggestion if you are going to be doing some future research on this.
Yeah,
Yeah, yeah,
I think that's a great point because
yeah,
I tried to keep my features very general, so they kind of just apply to any player. Um, and that could be a weakness in a sense because, like you said, there are certain trends that you can pick up with certain players. With a key one being how they perform on certain surfaces. That's a huge trend right now in tennis. Is there's the clay season just started, and there's a couple players who weren't performing very well on the hard courts, but are now performing great on the clay. It's just because it's their strength. So grouping those players together is definitely a really good idea.
yeah. All right, Gennaro, your mic is okay?
Okay, I think
Yeah, good.
you can hear me now? Okay, yes.
Yes,
Yeah.
yes.
So you mentioned deep neural networks, doing some research into those. Have you looked at any specific architectures in terms of deep neural networks, or did you just leave it at, general sort of classification tool?
Yeah, so the only real research I've done is just related work. And I did see that there was like a general structure they used to form their their deep learning, sorry, deep neural network. They had like the hidden layers and the whatnot, but I haven't done like specific research into actually architecting that those
Sure.
layers and how many neurons go in each layer and whatnot. I think that's just a bit over my head, considering my limited experience. But it's something I'm definitely interested in because I really would like to see these models understand on a deeper level things like the surface and the best of three, best of five, the level of the tournaments they're playing, and these models just weren't really picking up on that. So I would love to see if a deep neural network could see those correlations. But yeah, I've basically just seen some related work. I haven't done too much research on that otherwise.
Okay, then the follow-up question is, you mentioned that there's sort of a temporal component to your data set. What do you think is the effect of sort of the time point on the outcome, and how did you address that? How did you handle it in your work? Sort of two questions.
So I think one thing that is really hard to determine with tennis is how and this is something that's worth researching, is how has the game evolved over time? So, for example, predicting a match that occurred back in 1995 is very different than predicting one that's going to happen tomorrow, just because the game's evolved. Um, Naturally, because of like we talked about, the data needed to be split by time, so we had to train on matches that were older and then evaluate on matches that are newer, which could be a potential weakness because of the fact that the game has evolved. Um, does that partly answer your question? Sorry.
Mhm.
Okay. Yeah, so I think that's definitely something that is tricky, and I'm not exactly sure how to overcome that challenge because we can't introduce data leakage by, training on the recent matches that happened. So it's just a bit of a up in the air for me. I think that we would need to do more research into.
Do you think a player's game history at all influences or affects their future scores? Have you seen any indication that the data set shows that?
Like for example, do you mean like their last 10 matches? Like the way,
Sure.
yeah. So a very like common thing in tennis is that players get hot, and especially when it comes to the part of the season we're in, as well as certain tournaments, right? So there's a tournament that a player will naturally do well at, and it's part of kind of like a certain part of the season where it's like the hard courts, for example. So those last 10 matches will do a good job of saying how well is this player doing recently in that time window, which then does contribute, especially when some of those matches in that window fall into the same tournament that we're still predicting for. So it actually helps to say, how is this player actually performing at this specific tournament? So that's why that relevance is there. Players do excel at tournaments. So, for example, like I said, Rafael Nadal has won the French Open 14 times, Barcelona 10 times, Monte Carlo several times. So it's important to look at past performance. And that's why I think even introducing something like, how does this player perform at this specific tournament we're looking at right now would be very helpful as well. So yes, past performance is very important.
Good. Then knowing that, I would say that, of course, the work you've done is great considering where we started and the approaches you took. I would say that if you were to continue this project, there are special neural network architectures that are very time dependent, things like recurrent neural networks, LSTMs, and so on, that are able to learn patterns across time in this way. And so I think that if you were to consider this work, not only improving the data set, as Professor Chen mentioned, which would be a fantastic improvement, but also looking at these sort of models that can capture the essence of what you just explained to me, of being able to learn where they have these sort of winning streaks and predict their performance, in part using them, not as simple as saying, this person won 13 times, therefore they're going to win next time,
Right.
but sort of, saying they're more likely to do better in this
Yeah.
case.
Right. Agreed. 100%.
Yeah, so I think that's all the questions for me.
Awesome. Was there any other questions?
So if no other question, who is the host? Daniel, you are the host, right?
Yeah, I'm the host.
Can
Yes.
you transfer the host to Gennaro? We are going to have a committee discussion. We put you in the waiting room, and then after we discuss, we bring you back to give you the decision.
Okay. Perfect. Yeah, I just assigned the host to Dr. DeLuca.
Yeah.
And thank you so much.
Yeah.